Hello and welcome to the Unit 3 Section 4 video on perpendicular lines. So first of all, let's talk a little bit about the distance from a point to a line. Remember, perpendicular lines are two lines that intersect to form four right angles. The perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. Now the shortest segment from a point to a line is perpendicular to the line. This fact is used to define the distance from a point to a line as the length of a perpendicular segment from the point to the line. So for example, we're going to name the segment from P to AC, the shortest segment from point P to line AC. Well, that shortest segment is PB. Now we're going to write and solve an inequality. So we know that if this is the shortest segment, then we know that PA has to be longer. So the length of PA is greater than the length of PB. With that being said, x plus 3, which is APA, is greater than 5. Subtract 3 from each side, and you know x has to be greater than 2. For example 2, we're going to name the shortest segment from A to BC. So point A is here, BC is here, and our shortest segment is segment AB. Now, we know that AC has to be longer than AB, so the length of AC is greater than the length of AB. The length of AC is 12, and the length of AB is x minus 5. So we add 5 to each side, and you get 17 is greater than x. So in other words, x is less than 17. Now, let's talk about proving properties of lines. Okay? There are some theorems for perpendicular lines that can be used in proofs. The perpendicular theorem states if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. Remember, the only type of linear pair where the angles are congruent is if the angles are both 90 degrees, which means they're both right angles. Well, also remember that perpendicular lines form a 90-degree angle. So therefore, since the angles are congruent and form a linear pair, each angle is 90 degrees. And so in this case, we can say that L is perpendicular to M because these congruent angles are in reality both right angles. The perpendicular transversal theorem states that in a plane, if a transversal is perpendicular to one or of two parallel lines, then it's perpendicular to the other line. So here we are presented with two parallel lines. We are told that N is parallel to P. We're also told that Q is perpendicular to N. Since Q is perpendicular to N and N is parallel to P, then we can say Q is perpendicular to P. The converse of the perpendicular transversal theorem states that if we have two lines that are both perpendicular to the transversal or to the same line, then the two lines must be parallel. So this is the reverse of what we just did. So in this case, since R is perpendicular to T and S is perpendicular to T, then we can say that R is parallel to S. So let's do some examples of these. For example 3, we're going to determine whether each statement can be established using the provided figure, and we'll explain why. So for R is parallel to S, well, can we say anything about R in particular? We know that M and N are parallel because of these two right angles, so that tells us from the converse of the perpendicular transversal theorem that M and M are parallel, and that actually is what we're going to get to in part B here. But there are no right angle boxes indicating anything about line R. It could be just slightly off a vertical for all we know. So, since there is no indication that R is perpendicular to M, and it is notated that S is perpendicular to M. So let's see, let's figure out a little bit better way to say this. Since S is perpendicular to, I think I have too many things in here, perpendicular to M, but R is not necessarily perpendicular to M. R and S are not necessarily parallel. Okay. All right, for B, we had already mentioned that we know that S is perpendicular to M. So since M is perpendicular to S and N is perpendicular to S, then we can say that M is parallel to N. For S is parallel to T, well, again, since S is perpendicular to N and T is perpendicular to N, then we can say that S is parallel to T. Both B and C come from the converse of the perpendicular transversal theorem. All right, example 4. We're going to find the value of x when A is perpendicular to B and B is parallel to C. Well, these two are perpendicular, and we know that these two are parallel, then you know this also has to be 90 degrees. So if we know that, we can say that 5 times x plus 7 plus 15 equals 90, and we can solve it from there. Distribute, combine like terms. So that's going to give us plus 50. And then 5x equals 40, so therefore x equals 8. Now let's do some proofs. So in example 5, we're going to provide a 2-column proof for the following. So we are given 3 statements, and I am going to take those 3 statements and place them here as are given. So we have AD is parallel to BC. AD is perpendicular to AB. And BC is perpendicular to DC. So those are all givens. All right, let's see what else we have. Well, we know that AD is going to be perpendicular to DC. And we know that because of the perpendicular transversal theorem. So AD is perpendicular to DC. And that comes from the perpendicular transversal theorem. And then finally, we can say that AB is parallel to DC. And that comes from the converse of the perpendicular transversal theorem. All right, let's take a look at example 6. So we're going to have 8 steps in this proof. And the first one, as always, we are going to write down our given. We're told that angle 1 is congruent to angle 2 and that P is parallel to Q. And that is our given. Okay. Now, we know that 1 and 2 are going to be supplementary. And that is because they are a linear pair. And so part of the definition of it being a linear pair is that they are supplementary. So our reason here is from the definition of linear pair. All right, moving along, if we know that 1 and 2 are supplementary, then the measure of angle 1 plus the measure of angle 2 are going to be 180 degrees. And that comes from the definition of supplementary. It also comes from the linear pair theorem. And I think that may be the more appropriate one to list here. Okay, so let's look back at our given. We're told that 1 and 2 are congruent, so we know that the measure of angle 1 is equal to the measure of angle 2. And that comes out of the definition of congruence. Now, we know we can substitute in angle 1 for angle 2, so we can say the measure of angle 1 plus the measure of angle 1 equals 180 degrees. And that's substitution property. And we know we can combine the like terms, so we have 2 times the measure of angle 1. And again, anytime we combine like terms in geometry, we call it the substitution property again. Now, if we divide each side by 2, we get the measure of angle 1 is equal to 90 degrees. And that came from the subtraction property of equality, or I should say division property of equality, excuse me. And then finally, if the measure of angle 1 is 90 degrees, then we can say that A and Q are perpendicular, or Q and A are perpendicular. Because P and Q, we were told, were parallel. And the reason for this one, the perpendicular transversal theorem. All right, example 7. We're going to provide a 2-column proof for the information we're given here. So there's a lot of angles that are labeled in this diagram. We most certainly will not be using all of them. So let's start with our given. A is parallel to B, and C is parallel to D. And that is our given. All right, so now let's see what else we can say. Well, we're trying to get from angle 9 to angle 8. That's what we're trying to prove, is that they are congruent. 9 is here, 8's all the way over here. So let's follow a path to get there. Let's follow the path going down. So we know that 9 and 16 are congruent. So let's write that. Angle 9 is congruent to angle 16. And the reason for that is the alternate exterior angles theorem. Now let's talk about angle 16, and let's try to relate that over to 8. Well, they're in the same slot, so therefore they are corresponding angles, which makes them congruent. So angle 16 is congruent to angle 8. And that is by the corresponding angles postulate. And then finally, we can say that angle 9 is congruent to angle 8. And we get that because 9 is congruent to 16 and 16 is congruent to 8, so therefore 9 is to be congruent to 8. That is the transitive property. All right, one more proof to round out this section. So we are starting with our given again, and our given is that A is parallel to B, and angle 2 and angle 5 are supplementary. And of course, this information is our given. So now, since we know that 2 and 5 are supplementary, we can say that the measure of angle 2 plus the measure of angle 5 equals 180 degrees. That's the definition of supplementary. Okay, so now let's take a look at our figure. Well, we can make a relationship between 1 and 5 because 1 and 5 are corresponding angles. We know that angle 1 is congruent to angle 5. And that comes from the corresponding angles postulate. So since we know that 1 is congruent to 5, we can plug in the measure of angle 1 in place of the measure of angle 5. And that is the substitution property. So if angle 2 and angle 1 equal 180 degrees, then we can say that angle 2 and angle 1 are supplementary. And that again comes from the definition of supplementary angles. And then finally, that brings us around to the fact that L is parallel to M. Because if 1 and 2 are supplementary angles, they are also consecutive interior angles, and by the converse of the consecutive interior angles theorem, we can then say that L and M are parallel. Okay, so we've done quite a few proofs here. So hopefully you've got an idea of how some of these angle relationships work and how some of the parallel and perpendicular angles work and lines work and everything like that. So in the next section, we're going to kind of veer a little bit and give you a little bit of a review of some algebra topics, because when you have parallel lines and perpendicular lines, you can actually plot them in a coordinate plane. So we're going to review a little bit about slope, we're going to review a little bit about the equations of lines, and we're going to use those equations and slope to determine some equations of parallel lines and perpendicular lines. That's coming up in the next section.